In this problem, we're given some information about the changing thermodynamic properties of a liter of gas, and we've been asked to draw the process on a PV diagram, so a pressure-volume diagram. So this means we're drawing a diagram with pressure on the vertical axis and volume on the horizontal axis. So because the problem tells us that we're starting with 1 liter of air, and that volume of the air is decreasing as the process continues, I'm going to define my axis so that we have a maximum of 1 liter of air, and then I'm going to label the halfway point as well, since that's relevant in the description of the process. And here's our 0 point at the origin. We're not given any specific quantities as far as the pressure goes, so I'm going to define my pressure axis not as the pressure itself, but rather in terms of a ratio of whatever the current pressure is to some initial pressure, which I'll call P naught. So at its maximum point, there's going to be a value of 1 for when the pressure is equal to its starting pressure. In other words, this is the pressure value we're starting at. I'll label the halfway point again. And so now that we've got the axes labeled, now let's begin actually looking at what the problem tells us about the process. So we're told that we're starting with 1 liter of air, and then it is going to be cooled at constant pressure until the volume is halved. So we're starting with 1 liter of air, so we're starting along this point. And with our initial pressure value, that means that the ratio is going to be 1. So the upper right is where our starting point is going to be. So our starting point is going to be right here at the top right, with a volume value of 1 liter, and a pressure to initial pressure value of 1. And the liter of air is being cooled until its volume is halved. So the volume is decreasing. So the process is moving to the left in a horizontal line because the pressure is kept constant. So I'm going to draw a little arrow indicating that the process is moving to the left, and that is it for the first segment of this process. The second segment tells us that the air is allowed to expand isothermally back to the original volume. Now recall that isothermal expansion means that the temperature is being kept constant. Not necessarily the pressure or the volume, but just the temperature. And this is when things can get a little trickier, because it's not going to be as simple as just drawing a straight line. In fact, with isothermal processes, there tends to be, there's a curved line, where the hump of the curve kind of aimed towards the origin of the graph. So from the problem description, we know that after this isothermal leg of the process, we know that the final volume is going to be 1 liter. It's going back to the original volume. The trickier part is figuring out what the final pressure ratio value needs to be. And this is where we want to remind ourselves of what the ideal gas law says. Recall that the ideal gas law states that for an ideal gas, pressure multiplied by volume is equal to the number of moles of the gas multiplied by the ideal gas constant multiplied by the temperature of the gas. Now, we can assume that the number of moles is not changing, because nothing in the problem is suggesting to us that it should, and the ideal gas constant is just a constant. And again, because this is an isothermal process, the temperature is also being kept constant. So, for an isothermal process, that means that the pressure times volume value is also being kept constant. This is helpful for us to know, because what that means is that if something happens that causes the volume to be doubled, then the pressure must be halved in order to keep that PV value the same. So what's going on in this problem is that when the gas is allowed to expand isothermally back to its original volume is being expanded from half a liter to 1 full liter, so its volume is being doubled. So if the volume is being doubled, then in order to keep the PV ratio constant, the pressure must be halved. So, as this isothermal process moves along, we must be heading towards a point where the pressure value is half of its original, and the volume's just the same as it was before. So in other words, we should aim for this process to go right around here. We want it at a point where we can see that the pressure value has been reduced to half of its original value. And that's kind of what I've done here. So, and then once again, as usual, I'm going to write a little arrow to indicate the direction of the process. And there we go. And really, that's it for this problem. I hope this video helped you out. If it did, please consider subscribing, as that'll help me out in making more videos just like this. If you have a question or request, leave a comment down below, and I hope you all have a lovely day. Bye.